Netcasts you love.
From people you trust.
This is Twit.
Bandwidth for Triangulation is brought to you by Cashfly at CACHEFLY.com.
This is Triangulation, episode number 302 for Monday, June 19th. Michael Summers, Exoplanets. This episode of Triangulation is brought to you by Rocket Mortgage by Quicken Loans. Home plays a big role in your life. That's why Quicken Loans created Rocket Mortgage. It lets you apply simply and understand the entire mortgage process fully, so you can be confident that you're getting the right mortgage for you. Get started at rocketmortgage.com/triangulation. And by Betterment, the largest independent online financial advisor. For one low, transparent fee, Betterment gives you personalized advice and invests your money. For a limited time, you can get up to 6 months managed for free. Learn more at betterment.com/triangulation.
Welcome to Triangulation. It's the show where we gather the fascinating people and stories from around the world of science and technology and bring them to you. I'm Father Robert Balacer, the digital Jesuit, in for Leo Laporte. And today we have, a special treat for you. If you've ever been interested in the fields of science, technology, space, astronomy, you're going to love our guest. We have Dr. Michael Summers. He is a professor of physics and astronomy at George Mason University in Virginia, a planetary scientist who specializes in the structure and evolution of planetary atmospheres. He has his BA from Murray State University, an MS in space physics from the University of Texas, and a PhD from the California Institute of Technology in planetary science and astronomy. Dr. Summers, thank you very much for joining us.
Oh, my pleasure to be here.
Now, before we get into the reason why we have you here, which is a new book that you've written called, or co-authored, called Exoplanets. It's Diamond Worlds, Super Earths, Pulsar Planets, and the New Search for Life Beyond Our Solar System. I want to get a little bit of background about you.
Sure.
This is a very interesting time to be in this field. The last 3 decades have seen this, our corpus of knowledge about the outer planets, about extrasolar objects, be turned on its head. What brought you into planetary science all those years ago?
Oh, gosh. Well, I like to think that I became a planetary scientist when I was 6 years old. My father got me a very small telescope, and I didn't have a clue what I was doing with it. But I lived out in the country, so I could see the stars at night. And I took it out in our backyard, and I set it up and just looked around to see what I could find to see. And there was a bright yellow star in the sky. And I pointed the telescope at it, and you wouldn't believe it, but it was Saturn, the planet with rings. And you could see it. You could see a little globe there with little sort of lobes on the side, which were the rings, and I was just stunned. It was just a discovery. I mean, I discovered Saturn and for myself because I didn't know what I was doing. And to think about a planet that I could see that was a tiny dot, but yet 90 times as big as the Earth, and that if you brought it here and set it right between the Earth and the Moon, its rings would encompass both. And I was hooked. And I mean, when I was a kid and a teenager, I built larger and larger telescopes, up to a 12-inch telescope in high school. And then I went to college and I used their observatory. And then ultimately, I was so interested in planets, I wanted to find a way of getting into space exploration and study planets with in situ data, with spacecraft robotic instrumentation. And so that's when I got interested in going to Caltech and JPL. And when I was there, I had just amazing opportunities to work on various space missions. Voyager 1 and 2 had just passed Jupiter when I was doing my PhD thesis. So I was very lucky to get some first looks at the data from the moons of Jupiter. And Io was pretty intriguing. So I did my PhD thesis on Io. And as far as I'm aware, I wrote the very first paper ever on supersonic meteorology, supersonic winds on Io. And so that was kind of cool. Not a lot of applications at the time. We have them now because we see lots of planets with supersonic winds. But at the time, that was kind of a first. And then after Caltech, I got interested. Well, actually, while I was at Caltech, I got interested in Pluto. So ultimately, I was involved in the New Horizons mission to Pluto. I'm a co-investigator on that. I've worked on Mars missions, Venus missions, a variety of missions studying the upper atmosphere of the Earth and the chemistry, thermal structure, radiation of ozone in the Earth's atmosphere. And most recently, though, like many astronomers, we've been sort of taken aback by what we found outside of our solar system, and that is extrasolar planets. So, I mean, as you mentioned, the past few decades, our ideas have been just turned upside down. And that's kind of an understatement, if you will, because we were just so totally wrong. I mean, we really didn't have a clue.
Let's talk about that, because that is an interesting point. When I was growing up, I was being taught a very certain order of the universe. Yeah. We had it on good authority with some decent research that all of the universe, all of our galaxy at least, had solar systems that were constructed like ours. We assumed that they were going to have inner rocky planets. We assumed that they would have outer gas giants. We assumed that they would be very similar to what we have in our own system, and that's turned out not to be the case. In fact, one of your fields of expertise, which is the study of chemistry and the thermal factors on a planet, has really contributed to us understanding that things are much, much stranger in our galaxy than we thought.
Yeah, stranger. And the reality is we really didn't know when I was a kid, when I was in graduate school, we really didn't know if there were planets elsewhere. We guessed and we anticipated that based upon the laws of physics and what we saw in our solar system. But to see that there were planets elsewhere, but yet our solar system was not typical, there was two surprises. The large number of planets elsewhere is a surprise. The types of planets elsewhere have, continued to, astonish us. And I think that was what led to our writing this book. Is it's not just that the planets are different than what we see in our solar system. They're whole new categories of planets. I mean, not terrestrial planets, not gas giant planets, not dwarf planets like Pluto, but whole new categories of planets and dozens of categories. And so, and we're just on the learning curve. I mean, we haven't seen but just a hint at what's out there. At least that's what I expect.
Right. And it's not just that there are so many different types of planets out there, way more than we ever would have imagined. But one of the central tenets of our knowledge about Earth, that it was unique in that it had water. And you don't find liquid surface water anywhere else in the galaxy. That I think that is one of the hardest myths to dispel. That continues to this day. Even those who have read about the new planetary sciences and the developments in that field think, well, Earth is unique because of water. And now we know it's probably not as unique as we think it is.
Right. In fact, water is everywhere. Maybe not in stars, but there's ice on Mercury or on the moon. There's water underneath the soil on Mars. 3 of the moons of Jupiter have subsurface oceans of liquid water, each one of which dwarfs the oceans on Earth. Titan and Enceladus around Saturn have subsurface oceans of liquid water. We recently inferred that Pluto probably has a subsurface ocean of liquid water. And now we're finding whole planets. Think about that. Whole planets that are mostly water. Now, I'm not talking about, a water world where you have an ocean covering the planet. I'm talking about water through and through, from the surface, maybe 2/3 of the way to a rocky core would be an ocean, 10,000 kilometers thick. There's water just about everywhere, liquid water just about everywhere. That core ingredient of life that you learn in elementary school is all over the place.
I want to touch on something that is part of your expertise. I actually saw this on your CV. You were involved with New Horizons. You were involved in the search for exoplanets. Were you involved in the demotion of Pluto?
No, in fact, it caught me by surprise. Like many planetary scientists, we didn't realize what was going on when the IAU, the International Astronomical Union, voted for the reclassification of solar system objects. And so there was a lot of consternation about that, as you know. And and many of us strongly objected for really good reasons based upon physics. And in some ways it was unfortunate, but in other ways, the demotion of Pluto from planethood really triggered a lot of public interest in Pluto, and so there was a silver lining. Almost everywhere I go and talk to students, whether it's elementary school students, middle, high school, wherever, they want to know, why was Pluto demoted? Why is Pluto no longer a planet? Did it change? And of course, it didn't change. It was just a naming aspect of planetary science, which is important. But names are important,
right?
And this confused a lot of people. But it also opened up an opportunity to explain why naming is important, why studying Pluto is important, why these different categories are important. So it really developed a segue into talking about planetary sciences. And I've used that so many times, even though I disagreed with the decision, like many other planetary scientists, I was able to use that, leverage that interest into explaining what we're learning about the universe. And so I have to say that overall, even though it was a stupid decision, it was really an opportunity that we took advantage of, and it's helped a lot of generating a lot of interest in planets.
In our audience, talking about Pluto always brings up strong emotions, because there are those of us who say, well, Pluto was a planet when I was growing up, so it'll always be a planet. We have others who say, well, the reclassification makes sense. I love the fact that the very first time I ever heard of you was during the demotion of Pluto, and you made a public statement. You said, look, this could actually be a gateway to teach people about planetary sciences, because once you start looking at Pluto, you have to start looking beyond Pluto. And there is a fascinating collection of material beyond what we would consider the normal realm of our solar system within the Kuiper Belt. And can you describe the Kuiper Belt first? Because in your book, you talk about how there are masses, conglomerations of matter in that belt that can dwarf some of our inner planets.
The Kuiper Belt, just beyond the orbit of Neptune, has perhaps as many as 100,000 dwarf ice planets. Maybe I should say just dwarf planets. They come in different types, different flavors, if you will. There are large ones like Pluto, which may be largely ice, and then there are smaller ones which may be more metallic or darker or more carbon-rich. We're not sure. We haven't been close to those yet. But 100,000, think about that, 100,000 of these objects that we knew were there, but New Horizons gave us our first look at one of them. Every one of those is probably unique. How are we going to ever explore that many planets? It's unbelievable. But the educational aspect, as you mentioned, is really good, because when I was a kid, I'd never heard of the question, what is a planet? I'd never heard of that question. But now that we detect planets elsewhere at a rate of about 2 per day, that's the rate at which we're discovering new planets outside of our solar system. And with all these different types, the question about what is a planet is an important question. In fact, it's a key question. How do you organize our study? How do you organize our exploration of all these exoplanets that we call them outside of our solar system? Because there are more planets now known than there are planetary scientists in the world. And think about, spending all your life studying the Earth, and you would only just scratch the surface in what you could find out about it. And yet all these planets out there, 2 per day is what we're discovering. And that rate is going to increase. In 5 years, it'll be 10,000. In 10 years, it could be 100,000 with the new instruments that are going up. What are we going to discover then? How do we organize our thinking about them? How do we prioritize the detailed study of these objects to search for biomarkers, to search for life, to search for technological civilizations? There's a very rich set of questions about the study of planets that we're just getting our first look at. And I think Pluto, in a way, sort of was a hint at what was to come when we started studying exoplanets, because Pluto is so different than the Earth, but yet it has energy, it has organic matter, has liquid water like the Earth. So there are things that could be vastly different about some planets, but yet have commonalities that could be very key for life as we know it. So yeah, so what you bring up, there are a lot of different questions there, but this question of what is a planet is now a very key question.
We are speaking with Dr. Mike Summers. He is the author of Exoplanets, talking about Diamond World, Super Earth, Pulsar planets, and the new search for life beyond our solar system. We'll be taking up this question of what makes these planets, and actually a bit more on the Kuiper Belt. But first, let's take a moment for these messages.
If you're watching this show, then I am guessing you are a geek, the good kind of geek, the kind of geek that likes to throw technology at a problem and throw problems at technology. One of the problems that you could throw technology at is getting a mortgage. It is not easy to get a mortgage. It's frustrating. It's time consuming. You got to dig through old papers. You got to run around all over town. Why not make it easy with Rocket Mortgage by Quicken Loans? The mortgage experience wasn't keeping up with the times. It was dated, and it needed a client-focused technological revolution. And that is why Quicken Loans created Rocket Mortgage. Rocket Mortgage gives you the confidence that you need when it comes to buying a home or refinancing your existing home loan. It's simple. It allows you to fully understand all the details and be confident that you're getting the right mortgage for you. It's also convenient. They have trusted partners that allow you to share your financial information with Rocket Mortgage at the touch of a button. And it's powerful. So if you're looking to buy your first home or your 10th home, Rocket Mortgage is able to perform thousands of calculations in seconds. Based on your income, assets, and credit, Rocket Mortgage can analyze all of your home loan options for which you qualify and then find the one that is right just for you. Just right for you. Rocket Mortgage by Quicken Loans. Apply simply, understand fully, mortgage confidently. You can get started right now. All you have to do is go to rocketmortgage.com/triangulation. That's rocketmortgage.com/triangulation. Equal housing lender, licensed in all 50 states, NMLS consumeraccess.org, number 3030. And we thank Rocket Mortgage by Quicken Loans for their sponsorship of Triangulation.
And we're back with Mike Summers, author of Exoplanets. Mike, I want to talk a bit more about the belt. Your co-author of this book, Dr. James Trefil, he calls it, it's the construction zone, the materials left over after all the important buildings are done. And as you mentioned, you're finding 2 new exoplanets, extrasolar objects, every single day. Right. How is this changing your field? I mean, you're discovering more now than has been discovered in the previous 300 years combined.
I would say than the past 10 years. Everything before that combined doesn't match what we're learning every year now. And that rate of learning is going to go up. So that's having a pretty, I don't know, sort of a philosophical effect on how we approach the questions about planets. How do we study them? Because there are just so many of them. It's hard to know how to, like I said, categorize them, and then how to follow up categorizing planets with detailed observations that allow us to do what just about everyone is interested in, and that is to search for life elsewhere, life on these planets. So the questions are just all over the place. It's just too rich. I would have to say that right now we're overwhelmed. And that would be my response, is that right now we're just so overwhelmed with what we're learning that we haven't really come to grips with this new view of the solar system. And in fact, it's probably a little bit too early to try to even put together a big picture of what your average solar system is like, because there may not be an average. There may be just a huge diversity where, you know, there are 100 different categories of planets, and we're one of them. So, but we don't know. That's the thing that's neat about exploration, is that you're going to discover something, and it's not going to be what you expect.
Well, I think that's what's so exciting about this. You've destroyed that phrase, the average solar system, because we now know we don't have an average. We thought we did. We thought that most would look like what we have, but we don't. And actually, I do want to jump into the book there, because in discussing how you search for these exoplanets, you first started with how you detect them. Can we talk about this? Because everyone has seen the graphical simulation of looking for the gravitational perturbations as a planet revolves around a sun. We hear things like red-shifted. What does this all mean? What do you actually see when you're combing through the data that tells you that's an exoplanet?
Okay, yeah, really good questions there. Detecting planets around other stars, distant stars, is very, very difficult. I mean, if you were very far away and looking at the sun and the Earth, the sun would be about 10 billion times brighter than the reflected light from the Earth. So there's a contrast issue. And then the planets are so close to stars, it makes it almost impossible to detect planets around distant stars directly. We've only done that in just a handful of cases. What you described was an indirect method of detecting planets, and that is we use a measurement of the motion of the central star to infer the gravity tug from a planet orbiting it. So if you have a star and you have a large planet orbiting it, that planet tugs on the star. And we measure that tug, that motion of the star. And we're so sensitive now that we can measure the motion of a star down to about 1 meter per second, even if the star is 1,000 light years away. And that's walking speed. And so when you have a planet, that speed goes up and down as the planet orbits the star. So by looking at that period and the magnitude of the velocity, you can determine the orbital distance. You can determine the mass of the planet if you're clever. You can start determining the surface temperature of the planet. But that's all based upon an indirect detection of the planet. There's another method which has actually been a little bit more successful than that radial velocity method that you mentioned, and that is to look at the transit technique, where we look at that small percentage of the solar systems where the planets are in line with our line of sight, so that we can look at the planets move in front of the distant star. The planets will move in front of the star that they orbit. And so when they do, you see a little bit of dimming of the light from the star. And so the magnitude of that dimming gives us a measure of how big the planets are. The period of the dimming gives us, again, the orbital period. From that, you can use Kepler's laws of motion to get the distance. From that, and knowing a little bit about the star, you can get the surface temperature, and so on. And you build upon that indirect detection. However, in the past few years, we've made some progress in direct imaging of planets around distant stars. Only a few successes at this point, but that's going to be an area that's going to sort of be a growth industry, if you will, over the next decade, is detecting, imaging planets around other stars. Proxima Centauri b is the ideal example. The nearest star to the Earth has an Earth-like planet. And you can bet that every astronomer out there that studies exoplanets wants to be the very first one to get a picture of the nearest exoplanet to our solar system. Because when we start exploring other stars, that's going to be one of our very first stops. And there's going to be a lot of naming opportunities for discoverers there. But there are all these other planets that are interesting as well. The TRAPPIST-1 system that was announced a couple of months ago what is a system with 7 Earth-like planets around a single star, 3 of them in the so-called Goldilocks zone, where you can have liquid water based upon the temperature being right for liquid water to be stable on the surface. So 7 Earth-like planets in one system. Maybe there's a system out there with 100 Earth-like planets. I wouldn't be surprised.
Let's unpack that, because that's a fascinating application of physics and astronomy in order to be able to figure this out. Let's hold off on transit for a bit and talk a little bit about gravity, using gravity, the pull of a planet around its star to obtain data about the system. That only works if you have a sizable planet. How large, how many AU does a body have to be to exert enough gravity on a star that it makes it observable?
Well, that that observable criteria changes as technology gets better. When we first started using the radial velocity technique, we could only detect really big planets that were very close to the central star. So big gravitational tugs over short periods of time. And so the very first set of planets that we found were gas giant type planets like Jupiter and bigger that were in orbits of only a few Earth days. And that kind of shocked us a little bit because it's very hard to form a giant planet like Jupiter close to a star. But it turns out that those types of planets are really a minority. Only a few % of all the planets we've detected are really these hot Jupiter-sized planets that are hot because they're close to the central star and have close-in orbits of only a few Earth days. That's a very small percentage. As technology got better, we were able to measure smaller and smaller gravitational tugs on the central star. So now we're approaching the technology that's going to allow us to detect Earth-sized planets at distances up to about the distance of the Earth from the Sun. And over the next few years, you're going to see the first detections of Earth-like planets at such distances around some of the nearby stars. And that's going to be a pretty important development because then we can truly look at the numbers of Earth-like planets that are truly Earth-like that are out there.
Even with the improving technology that allows us to detect smaller and smaller events, combined with transit, where the planets have to be aligned in a very specific way so that they are in our line of sight.
Yeah.
It kind of tells me that even though you're finding all of these extraordinary objects, there's so much that we can't see. We're limited by the technology that we have, and we're limited by our location in our galaxy. So for everyone you're finding, is there an extrapolation I can make about how many I'm not finding?
Wow. Yeah. I mean, that's a question that many of us think about quite a bit. What is the average number of planets per star? And I mean, officially, you could do the formal statistics, and it's probably in the range of 4 to 6 planets per star based upon the data we have. But given that we're detecting smaller and smaller planets further and further out, my guess is the number is going to end up being somewhere between 10 and 20 planets around every star. I mean, every star in the sky that you see when you walk out at night is going to have 10 to 20 planets that are Earth-like, terrestrial planets, or gas giant planets. I mean, think about that. 10 to 20 for every star in the sky that you can see. Every star in the galaxy, on average, will have that many planets. And that may be just scratching the surface because there may be planets floating around between the stars, and that number could dwarf the number of gravitationally bound planets. But again, that's a little bit of speculation. We can extrapolate to some extent, but we're discovering planets, and our technology is improving at such a rate that we don't quite know where it's going to end up right now.
I want to talk about that technology in a little bit, but first let's dive into the book. Let's dive into exoplanets. Sure. I know that people have been proposing exoplanets for quite a while, but would you say that it was in 1992 that we first actually nailed down a confirmed exoplanet?
Yeah, there was this astronomer named Peter Van de Kaap, who studied the motion of a nearby star across the sky, and he had claimed that he had found wobbles in the motion due to orbiting planets. But that turned out to be spurious data, systematic errors in his observations. The first unambiguous detection of a planet outside of our solar system, in my opinion, and this is about a fairly good definition of what a planet is the few planets that orbit pulsars, and that in itself was another surprise. A pulsar is the end product of a supernova explosion, where a star converts a large fraction of its rest mass energy into radiant energy and neutrinos and gravitational waves and other things. And that kind of explosion should vaporize, should destroy any planets in orbit. But yet, there they are. We find planets in orbit around pulsars. And in the early 1990s, we found 2 very clear examples of this. So these were the very first detections and these were very far away. These were not close pulsars. You're talking about things that were 10,000 light years away. But because of their effect on the rotation of the pulsar, on the timing of the pulses, we could detect them pretty easily. So yeah, that was the first inkling, I guess, that the galaxy was going to be much stranger than we expected, because that was the one place that we did not expect to find planets, and yet that was the place where we found our first planets.
That was the part that's always fascinated me, because from what I learned about pulsars, they are the corpses of an incredible astronomical event. And there shouldn't be anything left. And of course, our audience is pretty well versed in science. And so they understand that there's a natural process within a star where you have the gravitational forces that are fighting against its desire to just blow itself apart. At some point, it runs out of material to fuse, and then you get yourself a supernova. But in the creation of that supernova, it should wipe out every planet in the system. So when your field started coming back and saying, we're finding planets that are circling pulsars, I'm thinking, how is that even possible?
Right. Yeah. I mean, many of us were very skeptical of the whole idea, but it was hard to refute the data. It's extremely clear. And so we're still trying to puzzle out how they can be. I mean, some people think that the planets around the star, when it went supernova, went nova, were actually destroyed. They were disintegrated, and then yet reformed later, a lot like planets form in the first process, where you have an accumulation of gas and dust and rocks and mountains and asteroids to form planets. So maybe it went through a process of reforming these planets around that star after it became a pulsar. That's a possibility. Another possibility is maybe the planets were much further out. They survived, and somehow they migrated closer to the pulsar. I'm not quite sure that one is really a very satisfactory answer, but it's possible. We can't completely rule that out right now. And then there may be something that we completely don't understand about supernova. Maybe they don't explode radially. Maybe that there are domains, regions that can survive the explosion. That's still a puzzle. You know, how can they be there? I'm not sure we have a really good answer to that yet.
I know we're supposed to be talking about exoplanets, but I do want to dive into stars just a little bit, because it's fascinating, the detail that you go to in your book. Specifically in science fiction, there's always a weapon that kills stars. There's always something that will destroy a star, make it go supernova. And in reality, that weapon's a lot more common than you think. It's iron. Once iron starts forming in the core of a star, it's doomed. Can you talk a little bit about the progression from large star? In other words, our star can't go supernova. It's not big enough. But a star that is large enough, how does it slowly start to fuse heavier and heavier elements until it can no longer fuse them? And then how does that lead to the supernova?
Well, as you form heavier and heavier elements, you do release energy in the fusion process, but the amount of energy that you release goes down as the element gets more complex. By the time you reach iron, you're pretty much at a break-even point where you can fuse to form iron, but you don't release much energy. And so very quickly you start fusing everything up to that point, and then there's nothing beyond that to fuse that releases energy. Now, the reality is that, yes, you could fuse larger and form larger elements, but it takes energy going into it to do that. You don't release energy. And in fact, in supernova explosions, you do form elements heavier than iron. But that takes energy to form. That's an endothermic process. So, and as you mentioned, stars hold themselves up by energy that's flowing outwards. That radiative outflux of energy keeps the star from imploding. And once it's out of that energy that holds the star up, it just implodes. And that process, I'm told, can be very quick. It can be just on the order of seconds. The time it takes a signal of light to pass through a star is about the time scale it occurs when that implosion starts. And you don't want to be around when that happens because it's going to be fast and it's going to be catastrophic.
Once you start getting to those heavier elements, it can fuse them, but they are now energy negative. So they're actually taking the energy generated by the fusing of lighter elements to fuse iron, to fuse those heavy elements, and eventually it can no longer sustain itself against its desire to explode. Okay.
Yeah.
Now, also continuing with stars, how big does a star need to be in order to go supernova?
Okay, you're a little bit outside of my field. I study planets, so here I would direct you to someone who really understands that field. But as you mentioned, our star probably will not go supernova, right. and you're going to need a star with several solar masses to become a supernova in general. But there are different kinds of supernova. There are supernova that go off sort of on their own, and there are supernova that go off as a consequence of interaction with nearby stars, and the variety of nova as well. So it's a complicated process, but I would say that and there are many parameters that are involved, but I would say that you need something at least a few times the mass of our sun for that to happen.
All right. Now let's talk a little bit about the technology. We have people who are asking us about how you do this detection. There are several fantastic tools that have been launched over the years, but I think none has been more important for the discovery of exoplanets as Kepler. Would you agree with that?
Yeah, Kepler uses it's a space telescope that stares at a portion of the sky and looks for planets going around the stars and dimming the light, the transit technique. And so that's what Kepler does. It looks for transiting exoplanets, and it's discovered thousands of them. And there are thousands more candidates that are potential discoveries, but we can't call them a discovery until that detection has been confirmed by an independent observatory, an independent telescope. So yeah, it's been incredible in detecting them. The additional thing that Kepler is capable of doing, which I don't think the public is probably as aware of, is that Kepler can use this transit, especially at transits at different wavelengths, to start getting an idea of the shapes of the exoplanets, of how temperature might vary on a planet around the planet from one side of the star to the other side of the star, and even get an idea of what the atmospheric extent might be like. And from that, you can get the atmospheric temperature. And those are difficult things to do. And we're doing these on the ground by ground-based telescopes quite frequently now. But the same technique, this transit technique, can be used to do more than just get the size of the planet and its orbit directly. It can get compositional information. By looking at the transits of some planets in front of the background stars, we saw the element sodium. We're seeing absorption that looks to be from water and from methane and carbon dioxide. So we're using that technique at different wavelengths to start characterizing the surface environments of these stars. So Kepler was our first, I think, big success in getting in and trying to figure out what these stars were like. The radio velocity technique it gave us the sense of how many were out there, where they were in their orbit, how big they are. But the transiting technique, it looks like it's going to be more promising in the long run.
We are speaking with Dr. Mike Summers. He is the co-author of Exoplanets, Diamond World, Super Earth's Pulsar Planets, and the New Search for Life Beyond Our Solar System. We will come right back to talk more about Kepler, but before we do that, let's go ahead and take a moment for these messages.
You know you should be investing for you or your family's future. You know it's the right thing to do, but you have better things to do. Monument Valley 2 just came out. You got to get all the levels. You don't need to be worrying about investing. And I don't even want to talk about the fees. So many fees with investing, and you never know. There is a better way with Betterment. That's why it's called Betterment, because it's the better way. Betterment takes advanced investment strategies and uses technology to deliver them to more than 250,000 customers. Betterment is the largest independent online financial advisor. Betterment's designed to help improve customers' long-term returns and lower taxes for retirement planning, building wealth, and other financial goals. Based on the information you share, Betterment will make tailored recommendations on decisions like how much to invest, how much risk to take on your portfolio, and the type of investment account that you should have. It's not just opinions. These are tailored recommendations with advanced investment strategies. On average, Betterment's tax-coordinated portfolio can increase portfolio value by an estimated 15% over 30 years. Betterment gives you a clear view of your net worth when you sync your outside accounts, such as bank accounts and other investments. So just put it all in there. It's secure. And then you can get an overview, like you're flying a plane over your investments, and you can see what you need to know. And then you can stop worrying about it. Another reason to choose Betterment: low, transparent advisory fees compared to traditional services. Only 0.25% on assets under management, with an option to upgrade to 0.4 or 0.5 for access to CFP or licensed financial expert. Betterment cares about keeping your money and your data secure, which is why they have advanced data encryption and login protection. If you want to talk to someone about your specific financial situation, you can access their team of licensed financial experts. You are not alone. They have people who can help. Investing involves risk. For a limited time, you can get up to 6 months managed for free. No reason not to try. For more information, visit betterment.com/triangulation. That's betterment.com/triangulation. Betterment, rethink what your money can do for you. And we thank Betterment for their sponsorship of Triangulation.
We've been speaking with Dr. Mike Summers. He is the author of Exoplanets, Diamond Worlds, Super Earths, Pulsar Planets, and the New Search for Life Beyond Our Solar System. Mike, Kepler. Kepler is a fascinating tool. It was launched in 2009 to, I'd say, some great fanfare in the scientific community. It was about the size of a small car, about 1,000 kilograms. It had a 478-kilo payload. But with that payload, they made something amazing. Tell me more about Kepler. This is a spacecraft that has really broken the rules about what we thought was possible for the observing of the universe.
Yeah. So Kepler is a telescope that is made up of a set of CCD cameras that just monitor the light from stars in a particular area of the sky. If you know where the constellation Cygnus is in the sky, just go and find Cygnus, and then look just to the east of that constellation, and you'll see a little patch of the sky, which is just outside of the plane of the galaxy, where Kepler is monitoring stars, or has been over the past few years. And so in that area that it monitors the stars, there are over 100,000 stars that it can detect, and it can measure the light. So you're really monitoring 100,000 star system, planetary systems. But the only planets that we can see there are the ones that, as we talked about, orbit in a plane that connects the central star and our line of sight. So everything else, there may be planets here, but we just don't see them. We only see planets in about the 1% or so of those systems that have to have a plane that is along our line of sight. But even so, we've now found thousands of planets around those stars, and so that is, I guess, in a nutshell, why it's so astonishing, because it's simple. It just monitors the light from these stars over time and looks for the dimming of that light from these stars. And from that dimming, you get all this information about the distribution of planets around stars, their distances, their sizes. And Kepler's not going to be the end of the story. We have another satellite that's going up next year, the Space Telescope, called TESS, and that's going to monitor light from stars, not from a small region of the sky like Kepler did, but TESS is going to monitor light from all the bright stars in the sky, well, most of them, the northern hemisphere and the southern hemisphere. The hope is that this telescope will reveal those planets that are Earth-like, that are around, say, the nearest 100 or closest 100 stars to our solar system. And then once they are detected by TESS, the follow-up study of these objects will be from either ground-based telescopes, so have some really big ground-based telescopes now, or the James Webb Space Telescope, which it too is planned to be launched next year. And then it will go a shakeout phase. Then probably in 2019, we'll be using that to study these exoplanets. So, yeah, I mean, Kepler is astonishing for many reasons, and the types of planets it's found is intriguing, but the technique is going to be expanded over the next few years with another space telescope that uses the same technique, and that's going to hopefully find a few hundred candidates of planets that are truly Earth-like, that could potentially have Earth-like life as we know it.
Oh, you mentioned that Kepler is pointed towards Cygnus, which that actually surprises me, because if I remember correctly, and I might be wrong here, Cygnus is not the most densely populated area of our sky. Yeah. It would seem to me that you'd point the telescope at the place where it could see the most. Why is it pointed at Cygnus?
Well, if you live in an area where you can see the Milky Way at night, you can probably figure out the answer to that question. The Milky Way passes right through the constellation Cygnus. And in the Milky Way, you have a lot of stars, but you have also a lot of gas and dust. And in fact, the stars are so close together that you have to begin to worry about overlapping signatures. You want to look in a region where there are a lot of stars, but you don't want to look in a region where the stars are too close together, or there's a lot of gas and dust that can cause problem in the interpretation of the dimming of the light. And this region was sort of the best of both worlds. It was close to the plane of our galaxy, but just enough outside of it so that the density of stars was not too high to prevent clear, unambiguous signatures of planets.
Oh, another interesting thing about Kepler is the fact that it's not orbiting the Earth. It circles the sun every 372 days, which means every year it falls further and further behind. It's trailing Earth. Why did we do that? Why is that the orbit that the telescope's in?
Well, there's several things. I mean, one is that if you have a telescope in Earth orbit, it's true that you're above the atmosphere, that you don't have to worry about atmospheric scintillation effects, turbulence, and that kind of stuff. But on the other hand, you do have a day-night effect, which can be very complicating. For instance, you never want to point a sensitive instrument, an optical instrument, at the sun, because that can burn out your optics. And so you want to look at the sky. And if you're orbiting the Earth, you've got to continually change your look angle. That takes a lot of overhead for a spacecraft. Now, if you take that same telescope and put it away from the Earth, where you can just point it at the same place in the sky continually without having to worry about the orbit of the sun or the orbit of the Earth around the sun, or the possibility of looking at the sun by mistake or something like that. You can just stare then at that place in the sky continually. And that's ultimately that's one of the driving reasons for getting a telescope out of Earth orbit further away, so that you don't have to deal with the problems with 90-minute orbits where you have to continually change the positioning of the spacecraft. And that's a hard thing to do. I mean, especially when you're looking at something that's real far away, you're measuring very small signatures of dimming of light, and fluctuations, glitches, background noise, all of those can lead you to deduce that there might be a planet there when there really isn't a planet there. These false positives that you hear a lot about. And so having a telescope away from the Earth, away from Earth orbit, really solves several of those problems.
Something else about Kepler that a lot of people may not realize is we're actually on bonus time now. Back in, was it 2012, one of the reaction wheels died. Those are the gyroscopes, the fixed gyros inside that we can torque in order to rotate the satellite. Now, that one was the backup, so it just meant there was no backup. But then in 2013, just less than a year later, one of the remaining 3 failed. And I remember thinking, well, that's it. I mean, if you can't maintain your spacecraft in 3 dimensions, then it becomes useless, especially something like a telescope. But they managed to find a solution to operate it with 2 reaction wheels. How did they do that?
Well, engineers are very clever, as you know, and so it's interesting that you can repurpose a spacecraft when its primary purpose can no longer be accomplished. I find that really intriguing. In the case of Kepler, the problem is that you lose that control to point and to hold it stable with the reaction wheels. But you can harness other physics that's going on. For instance, sunlight exerts a force on a spacecraft. The solar wind exerts a force on a spacecraft. So why not use that to help positioning and hold a spacecraft in a certain orientation to look at distant stars? Now, if you're clever enough, you can harness those kind of things and use an external force to help control the pointing of a telescope. I just find that just incredible that they were able to do that for Kepler. But yet there it is, the K2 mission that now, without reaction wheels, or at least without the full set, is now able to accomplish an extended mission. It's a different type of extended mission, but nonetheless, it's still allowing us to use that telescope to detect these transits.
I have a friend at NASA Ames, and he tried to explain it to me as saying, imagine a boat tacking into the wind. So NASA has tacked Kepler into the wind, and it can use its remaining 2 reaction wheels to just sort of stabilize that position. But this does mean that the position is fixed, right? Because they can't turn Kepler without changing the pressure of that solar wind.
Yeah, right. I mean, the solar wind and the solar radiation, you can't control that at all. I mean, there is a little bit of fluctuation in the solar wind, but not much. So you have to work with what's there. This is an external thing that you have to really just accept and design your strategy around that. And so your friend is exactly right. You have to sort of tack into the wind, in a sense, to go in the direction that you want to go. Now, even given that, there's a little bit of flexibility in tacking. I mean, you don't have to tack in just a given direction. You can maneuver just a little bit. But here, the problem is really simple. You just want to stare at the stars. I mean, that's all you really want to do, to stare at the stars and look at their light and look for dipping in the light signature that's due to the transiting exoplanets. Of course, I'm oversimplifying. There's a lot more that's involved here. But that's really the goal. You just want to stare at the light and measure the light as a function of time. And so if that's your goal, then you can use these simple external forces to help position and control the Kepler telescope. Now, if you wanted to slew the telescope to another part of the sky, that probably would not be possible. Maybe in some cases it would, but most likely it wouldn't be possible because, again, you only have that external force which you don't control to use to orient the telescope. A little frustrating, but not greatly so, because we've got an extended mission which we wouldn't have otherwise.
We are all looking forward to the next space telescope that they put up, but how much more life can we get out of Kepler? I mean, even stuck looking at one patch of space, it's still bringing back incredible data. Is it another reaction wheel is going to bring it down? Will it run out of power? What is the thing that will kill Kepler?
Well, yeah, that's actually a good question. And I don't know the answer to that. It could be any number of failure modes that could prevent the processing of the data, the orientation of the spacecraft, some glitch in the computers. I mean, the thing with space exploration is that any kind of glitch is dangerous. You don't want to have anything go wrong. So yeah, another reaction wheel failing could be a problem. Any kind of radiation damage in the wrong place could interrupt the commands that allow us to harness this external force from the sun. But I bet that we're going to be surprised at how it fails, quite frankly. We don't know how long we're going to be able to continue to use it, but I just consider it a blessing that we have this extended capability, and be thankful as long as it extends. If it's another day or another 10 years, we just be thankful and go on, because we're living with Kepler on borrowed time. But predicting how it's going to fail, it might be a little bit difficult.
We've talked a little bit about the technology. We've talked about you and your passion for the planetary sciences. We've talked about how our knowledge has changed over the years. Now, let's get to the truly odd, the truly strange, the truly weird, the actual exoplanets. Now, in your book, you dedicate 5 chapters to talking about 5 exoplanets that have been discovered or postulated. The first one I find quite possibly the most fascinating. It's a world that is circling, is it 55 Cancri? How do I say that?
Yeah, 55 Cancri E. It's it's a planet that is larger than the Earth, probably somewhere between 5 and 7 times as massive as the Earth. It's in a nearby orbit of 55 Cancri A. A is always the central star. B is the first planet detected around it. C is the second, and so on. And the orbit is so close that E orbits the star about every 18 Earth hours. So think about that. 18 Earth hours, less than 1 Earth day, this planet orbits its star. That's its year. Which means that it's very close, obviously, and it's probably so close that it's really inside the outer atmosphere of the star. It's in the corona. It's moving away around the corona, and so there's probably a lot of very interesting fireworks going on there when that stellar wind is hitting the planet and its magnetic field. The thing that a lot of people find very intriguing about Cancri E, 55 Cancri E, is that if you look at its size and its mass, things that we know reasonably well, and then we do a computer model of different materials, what might make up the planet and give us that mass density, you find that we can fit the explanations, or we can fit the mass density very well with carbon. 6 protons, 6 neutrons in a carbon atom. And if the thing is mostly carbon, you can do a pretty good job of explaining the density of this planet. Now, what does that mean? Of course, carbon, low pressure, everyone knows is graphite. But at high pressure, carbon becomes crystalline. And that's how we get diamonds. And inside of Cancri E, then, you have most of the carbon. If it is carbon, again, we can't be positive. It may be 90% carbon, it may be 10% carbon, but to some extent, it doesn't really matter. There's a lot of carbon there at high pressure, and so you're going to get crystalline carbon, which is going to be diamonds at high pressure. So think about the Earth, 10% of it being diamonds. That would be kind of interesting. But it gets more interesting, because being a bigger planet, that means that the diamonds in the interior are going to be under huge pressure, over 100 million times sea level pressure. At those kind of pressures, even diamond would flow as a liquid, which would be astonishing. Now, most likely it's not pure carbon. There are going to be other things there, metals, nickel and iron. There are going to be things like silicon and oxygen there. And when we really get the final answer in its composition, it may be something we don't really anticipate. But right now, it looks like this planet and maybe a couple others can be explained by having a huge chunk of their interior being elemental carbon. That doesn't mean that it's by any means inhospitable to complexity. It may be inhospitable to life as we know it, but carbon is the backbone of the biomolecules of life. What kind of complexities might you get on a planet where you have that kind of energy and that abundance of carbon available for doing complicated things?
I think this is the part of the planetary sciences that just, it absolutely fascinates me, because we're talking about a planet that shouldn't exist in a system that shouldn't exist. This is a 4th generation star. versus ours, which is we probably think is a third-generation star. It's 7.9 billion to 8.4 billion, somewhere in that range, years old versus half as much for our sun. It is a higher concentration of heavier elements. You're talking about a planet that's 3.8 times as massive as Jupiter, only 5.8 AU from the sun, with temperatures on the surface approaching 2,000 degrees, receiving 3,000 times as much radiation as the Earth does. And then you've got a diamond crust and a liquid diamond core. It sounds so fanciful. How is it that you draw forth these conclusions about what must exist there? I mean, I know we've talked a little bit about how you can observe it and you can see what is what and how fast things are moving around. But then how do you make that leap from this is how close it is, this is how massive it is, this is how hot it is, to it's a diamond world?
Yeah. Well, the answer is physics. We know the laws of physics pretty well. And so we use the same laws that work here and work at other places in the universe to predict what the environment's going to be like in 55 Cancri E. Now, the limiting piece of our understanding here in this particular case is knowing more accurately its density. That means we need to have better measurements of its radius and better measurements of its total mass. Once we have better measurements of its density, then we can determine its composition a little bit better. So I actually wasn't the one that used Diamond Worlds as the subtitle of the book. That was the publisher. But on the other hand, there could be a huge amount of diamonds there. We just don't know a lot to go too far down the road in prediction for a planet like this. Until we get better observations, we just have to be kind of tentative and say, well, gosh, that looks like it could be carbon. Maybe it turns out that it's a lot of carbon monoxide, or maybe it's metal and rock like the Earth, and a lot of carbon. So there are a lot of possibilities. We can't eliminate a lot of things just yet. Now, one thing you did mention was the temperature. Having a planet this close to a star can receive thousands of times as much energy as we receive from our sun, and if you go outside our atmosphere, you get over 1,000 watts per square meter of light from our sun. You go 100 times closer to the star, you get 10,000 times higher energy flux. And so by the time you're getting a planet like 55 Cancri E down into an orbit so close to a central star, you're going to have surface temperatures of above 2,000 degrees Kelvin. So if you have rocks on the surface, they're probably molten. You could have a magma ocean on the day side. But the other interesting thing is that for planets this close, they can be tidally locked to the central star. And that means that they're somewhat like the Earth and the Moon. Whereas the Moon goes around the Earth, it always has the same face facing the Earth. So we had never seen the other side of the Moon until we had spacecraft go there and take pictures and send them back, because on Earth you always see that same side of the Moon. On a planet like 55 Cancri E, you have a somewhat similar situation. Most likely, it's going to be tidally locked, and it means one side is going to be hot, 2,000 plus degrees. The other side is going to be very cold. Could be down to 200 or 300 degrees Kelvin. Now, what it ends up being is going to depend upon whether or not you have an atmosphere, whether or not the atmosphere in a magma ocean can carry energy from the day side to the night side. In fact, even the shape of the planet is probably going to be distorted by being so close to the central star. It may not be spherical. It may be oblate, or it may be like a football. So there are a lot of different things that can affect the details of this particular system, which we're going to sort out over the next few years. But just to mention one speculation that is kind of interesting is that one of my grad students worked with me, and we found that you could actually get planets in the shape of a football in some of these systems. Now think about what an atmospheric meteorology would be like on such a planet. A planet in the shape of a football, always having its point towards a central star. Bizarre.
Oh my God, I love this. Now, but let's move on from the diamond planet to something that I've always found fascinating. That is this idea of rogue planets. You mentioned it earlier when you were talking about the Kuiper Belt. Have we actually spotted any rogue planets?
There are, a very few cases of rogue planets in the interstellar medium, and we detect those by a completely different technique, and that's called gravitational lensing. Whenever you have a planet moving in front of a background star, the gravity from the planet can bend the light from the background star. In some cases, you get a focusing effect. It's a gravitational lensing. You focus the light. And as the planet moves in front of the background star, you get a profile of how that light varies during the lensing event. And from that, you can get an idea of its mass, its size, and then you can start doing the inferences about the details of the characteristics of the rogue planet. So we don't have very many cases of these just yet. Okay, they're hard to detect. Rogue planets are incredibly hard to detect. As you know, planets don't generate their own light, visible light. We see most planets on Earth by reflected sunlight. Now, it is true that planets like Jupiter and Saturn and Uranus and Neptune emit more energy than they receive from the sun, but not in visible light. Most of that is in the infrared part of the spectrum. So when we look outside of our solar system for rogue planets, it's kind of hopeless to look for reflected sunlight. There's just not enough reflected starlight to see them. So if you use either gravitational lensing, or you try a completely different approach, and as you look for their thermal signatures, you look at their thermal emission or their radio emission, and that's going to be a growth industry as well over the next decade or so, because these take very large and infrared instruments, like the telescope that's going to follow on James Webb. WFIRST is going to be an infrared telescope, a large infrared telescope, the same sort of overall category as James Webb, and it's going to hopefully it will be able to detect a few of these rogue planets. But as I say, they're very difficult to detect. But having said all that, the fact that we can detect any at all suggests that they're abundant, and that probably shouldn't be a surprise to those people who've thought about the origin and evolution of planets, because the planet forming process is not a gentle process. Planets accrete out of gas and dust around a nebula just after the star becomes a main sequence star. And as they grow, they collide, and sometimes they refragment. Sometimes they grow into planets and they'll survive for 100 million years, and then they'll have a gravitational interaction with another planet that slings them out of the solar system. Or sometimes you could have a system of planets in independent orbits that their integrated perturbations build up into an unstable set of orbits, and they disperse, and some of them disperse into interstellar space. And any of those kind of things could lead to a planet escaping the gravitational attraction of a central star. And if you look at our solar system, you even see hints that these kind of things have happened. Like Mercury, for instance, it has a composition mostly of nickel and iron with a small layer of rock around the outside edge. It should have more rock. It probably doesn't, because it suffered a collision with another planet, which stripped off the rock from it and left behind the crust of rock that we have, a thin crust. That's all that's left of that collision. Venus probably suffered a collision or a nearby collision with a nearby planet, which either flipped it over or reversed its spin. Probably the Earth. Well, we know the Earth suffered a collision with another planet that formed the Moon. There's some thinking that Mars was in a near encounter with another planet that formed the Tharsis Bulge. Uranus is tilted on its axis by 98 degrees. That was probably due to a collision with another planet, a large one. Pluto and its moons, its 5 moons, were formed by a collision with another planet. Now, each of these collisions could destroy the objects, or it could sling one of them into interstellar space and the other one reaccrete and re-evolve. So we have examples there that collisions were common, and in many these types of collisions and rearrangements of orbits, you can have planets ejected. One I failed to mention is that there's indirect evidence that the orbits of the outer planets, especially Saturn and Uranus and Neptune, went through an interchange event early in our solar system history. That may have ejected a gas giant planet. So right there you have maybe a half a dozen planets from our solar system that could have been ejected into the interstellar medium. And those we have evidence for. There are probably many more encounters or nearby collisions that we don't have evidence for. But we don't know enough about what's out there really to work backwards and say how frequent collision-inducing escapes are. We don't know enough about that yet. We need to find some of these rogue planets and study them. And to me, the rogue planets are probably the most intriguing of all the planets that we talk about in the book, just because they're not dead. The one thing they're not is dead. I mean, it's easy to think about these as being cold, distant, boring objects, but they are not.
Oh, I also find them one of the more fascinating parts of your field because of how lucky you have to get to detect them. The detection methods that we spoke of at the start of the show involve the planets moving in a predictable path around a star, so that we can either measure the gravitational perturbations or view it as it passes across that light source. You're talking about being in the right place at the right time to witness gravitational lensing. And you're right. The fact that you found any suggests that there's probably a way more than we would have imagined. But you also filled in a part of a gap, a lacuna in my knowledge about these planets, because, again, I was always taught planets only form inside of a gravity well. So there has to be a star, something that will help to accrete the matter. And then it always bothered me. Well, how do they break free if they are bound in this orbit? You're right. Either it's got to be one part of the galaxy slamming into another part and enough gravity being exerted to sling it out of its regular orbit. And if you start to think of it that way, there could be way more of those planets than the ones that we consider regular planets.
Yeah. Now here we're getting into very speculative territory. There have been a few papers published trying to extrapolate to determine how many rogue planets there are. And of course, with just a few detections, that's really hard to do. We could have been lucky and found the only 3 rogue planets in existence. I don't think that's true, but that's a possibility. So the statistics are not very good. But accepting that, the extrapolation suggests that there could be as many as 10 times the number of bound planets that are what we'd call rogue planets, or there could be 440,000 times more rogue planets than are bound planets. Now, what I mean by that is for every one planet that's bound, gravitationally bound to a central star, there could be somewhere between 10 and 40,000 rogue planets. Now, what's the ultimate answer? We really don't know. But my sense is that there's a lot of them out there. Probably so many rogue planets out there that's going to completely change our notions of interstellar travel. I mean, if the larger numbers are correct, there could be a dozen rogue planets between us and Alpha Centauri that would be somewhere along the trajectory that we would take if we went to Alpha Centauri. And so instead of building a generation starship to go to Alpha Centauri, we travel a few thousand astronomical units, stop off at a rogue planet, refuel, get some resources, maybe colonize, set up an orbiting fusion star, and then move on to the next one, and then move on to the next one. And the steps are smaller, but we could still colonize the galaxy with much less energy and resources than what we would do if we had to hop between the visible stars. Now, again, speculation. We don't know just yet. We've got to find some more and study them.
Now, in your book, you do cover 3 other types of exoplanets. You talk about the ice world, about Kepler 186f, which is orbiting a M-dwarf star, as well as Gliese 1214b, which is a water planet. But I want to move to something else that you spent the latter chapters of your book on, which is one of my favorite discussions, and that is the search for extraterrestrial life. Of course, we're bringing up the Fermi Paradox, and to talk about the Fermi Paradox, you have to bring up the Drake equation. It's that is one of my favorites because it's a little bit of science and a little bit of pure imagination. Of course, we're talking about the active number of communicative extraterrestrial civilizations is equal to the average rate of star formation in our galaxy times a fraction of those stars that are going to have planets times the average number of planets in that fraction that can potentially support life, multiplied by the fraction of those planets that develop life, multiplied by the fraction of those planets on which life becomes intelligent and civilized, then by a fraction of those civilizations that develop space-detectable communications, and finally, the length of time over which those civilizations generate detectable signals. And according to that equation, even with all of those fractions of a fraction of a fraction, there are an untold number of systems that should have communicative extraterrestrial societies. And so the Fermi Paradox looks at the Drake equation and says, if it is that big, if there are that many, why have we not yet found them?
Right.
What's your take on Fermi versus Drake?
Well, the Drake equation first. I'm glad you put it up there because that summarizes the factors that we think are important in determining the number of advanced civilizations that are out there. When Drake put this equation together, only one of those factors was really well known, and that was the rate of star formation. Now, we have a good handle on the next two factors, the fraction of stars with planets and the number with Earth-like planets. And think about that. The fraction with planets is probably 1. The number of Earth-like planets is going to be greater than 1. When I was a kid, we didn't know if those numbers were 1 out of a million or what, okay? So we made a lot of progress since Drake put that equation together. Unfortunately, the other factors we still don't understand. We don't know the likelihood for a given planet to develop life. We don't know what fraction of those would develop intelligent life or civilizations or how long civilizations last. Those 4 things are still highly uncertain. So those we have to guess at. And those are it. I mean, that's it. The guesses, we just don't know. But if you put in what you might call optimistic or pessimistic guesses for those things, it doesn't matter. You get a large number of planets with life, a large number of planets with intelligent life, and so on. And it's hard to escape that conclusion. I mean, just the things that we've talked about here. If there are 10 planets per star, there are 400 billion stars in our galaxy. 400 billion is larger than the number of people that have ever lived and walked on this planet. There are 10 times that number of planets that are around these stars, and there may be 100 to 40,000 times that number that are floating around in the interstellar medium. And that's just our galaxy. I mean, if you extrapolate this to the visible universe, there are more habitable Earth-like planets than the number of heartbeats of all the people that have ever lived on this Earth. Okay, so the numbers are just overwhelming. So could we have all those habitable planets without life developing, without intelligence developing, without civilization developing? Many of us think, no, there's got to be life out there. There's got to be intelligence and civilization. And then the only thing left then is how long do these civilizations last? Again, something we don't know because we have only one civilization and we don't know how long we're going to last. It's possible to be optimistic and pessimistic there as well. So the numbers are huge and highly suggestive that life is common, but we don't know. Now, this is where Fermi comes in. If life is common and intelligence is common and civilization is common, then where are they? Because it only takes one advanced civilization that starts colonizing the galaxy, even if it takes 10,000 years, say, for a civilization to colonize the 10 nearest stars. And then each of those, it takes 10,000 years to colonize their nearest 10 stars. In 100,000 years, you've colonized the galaxy. And 100,000 years is a tiny, tiny fraction. It's a blink of an eye in galactic history. So the idea is, behind the Fermi Paradox, is that if there are intelligences out there, civilizations out there, then why haven't we seen them? Where are they? Or, are they hiding? And the literature is just, packed with possible explanations of the Fermi Paradox. It's like every week someone sends me a new article saying, well, this is a solution, or this is a solution, or some combination of solutions. The bottom line is we don't know. You asked my sense, though, my take on it. My take on it is that we're too stupid to know what to look for. Now, I think there are good reasons for saying that from several different perspectives. One is that we tend to be very parochial in determining life. Life, as we know it, is what we think about. Life that is intelligent and that thinks and philosophizes and colonizes the galaxy the way we might do it if we were out there. But those are speculations in themselves. We don't know what an intelligence could be like. Life might even be carbon-based. Maybe it's maybe there's a form of complexity on a surface of a planet that becomes super intelligent, 10,000 times as intelligent as the smartest human that's ever lived, and yet those entities are considered dumb on a galactic scale. So, intelligence, is something that we only have one example of. Complexity, maybe you can have complexity on a planet that doesn't have liquid water. Maybe you don't need carbon. Maybe you could do it with silicon. Maybe you could do complexity without silicon or carbon. Maybe you could do complexity with electric fields. Inside of a metal planet that's superconducting. Maybe spurious electric and magnetic fields could evolve by a form of Darwinian evolution, and you could get complexity, sentient, self-aware entities there that are 5,000 times as aware as us, and yet they wouldn't even meet any of our definitions of life as we know it on Earth. And so here I think that we're really suffering from an appalling sense of ignorance, about what life could be like, about what complexity could be like elsewhere. And even beyond that, how would a civilization communicate? Would they use radio waves? When I was a kid, the idea was that you would communicate from one civilization to another with radio waves, with radio transmitters. And that's an easy way for us to look for signals from other planets. But it's a highly inefficient way of communicating. You lose most of the energy. Why not use lasers to point directly at another solar system and send a signal that way? Much more efficient. But maybe even lasers are not the preferred means of communication for an extraterrestrial. Maybe they have some other way of doing it. Or, whatever. Who knows? The thing is, who knows? We don't know what they will be like, what they will think like, what they will desire. Maybe they're not interested in traveling. I have friends who don't like to travel. Maybe civilizations as a rule don't like to travel. Maybe it's an incredibly dangerous universe out there, and traveling is not a safe thing to do. Maybe it's safer to keep your head down and not let other civilizations know you're here. We're ignorant on all of these fronts. I suspect, like everything else, when we find intelligent life, we're going to be astonished. We're going to be surprised. It's going to be something, again, that was completely unexpected. It's going to open our eyes to another way the universe can generate complexity and intelligence and self-awareness. Sentience could be an outgrowth of complexity in ways that we can't even imagine. Our example of life on Earth could be one of a virtual infinite number of possible complexities that could come out of our universe. And most of them are so vastly different than ours that we can't even comprehend. So where does that leave us? I think we just have to look and see what we find out there. Keep exploring. We don't really know quite what to look for. That's just, it's frustrating, but we don't. We don't know how they communicate, how they think, where they would be, where they would travel, how they would travel. And to think that we've got, all the best explanations of the Fermi Paradox, I think is a little bit arrogant. But most people that think about this stuff that I've talked to are not very arrogant. They realize that we don't know enough. I mean, I'm not saying anything that's new here. Biologists say, well, other creatures are going to think differently. That's a given. We can't assume that they're going to have the same way of thinking or communicating as us. We're going to be completely different in that respect. And so to think that they have the same psychology is just plain nonsense. We just don't have any basis for that at all. And another piece of the answer, and I think this is probably true, is that we've just in the past decade or so started looking. I mean, looking for radio waves, as I said, is probably not a very smart way of communicating. It's probably a very unlikely way of getting success, of detecting extrasolar civilizations, communicating. Again, we don't know. Maybe that's the preferred means of communication out there. I doubt it, but it could be so. But we've just begun looking. I mean, we don't even know for sure what kind of biomarker to look for on a distant planet to say that there's biology there. Okay? I mean, detecting and proving that there's biology on another planet is not as trivial as you might think. I mean, we detected methane coming out of the subsurface of Mars, and there's been a lot of speculation for over a decade that could be due to bacteria underneath the surface of Mars producing methane. But we don't know yet. We're going to have to study that methane a lot more than what we've done so far to know if that really is due to bacteria coming out of the subsurface of Mars, due to methane from bacteria coming out of the subsurface of Mars. Sorry, I get a little bit excited with this. I start talking. My thoughts kind of run together because there are just so many possibilities that we can't evaluate. I mean, we're beginning to, but we just haven't gotten there yet. We've got, this next few decades, I guess, is going to be very informative in filling in more of those parameters, hopefully. Understanding the origin of life on Earth a little bit better. I mean, everything that we seem to understand about the origin of life on Earth seems to suggest that it's a very efficient, rapid process. Perhaps it occurred on Mars and was transferred to Earth and to Venus and to the moons of Jupiter, or maybe it originated on the Earth and that's it. Until we understand that mechanism, and then extrapolate that mechanism to other systems, other planetary environments, I think we're going to be pretty weak in our deductions about what's possibly out there. And in fact, I suspect, again, my take is that it's going to be beyond what we expect. I mean, it's just like everything else in space exploration. We're always surprised. We're always astonished. We're always stunned at what we find. If you'll indulge me for just a minute talking about the New Horizons Pluto mission, I spent a big chunk of my career helping to plan and carry out that mission. I started thinking about Pluto when I was a graduate student in 1984. And the flyby didn't occur until 2015. That's a lot of time to invest thinking about another planet and planning and preparing and carrying out a mission. And I was on a team of the most knowledgeable people in the world about Pluto. Couple of dozen of us that had spent much of our career thinking about Pluto. And yet every single one of us was astonished at what we found when we got there. I think almost all of us thought it would be a dead, interesting, but not vibrant planet. And yet there we find an atmosphere which we still can't understand. We find glaciers of nitrogen ice next to fields of hydrocarbons that are a thick organic goo. We find a layer of nitrogen ice lying on top of an ocean of liquid water. We find evidence that the whole system has evolved from a giant impact between another planet and it, which formed Charon and the other 4 moons. And it just goes on and on. We don't even know what the heat source is that keeps the things liquid, keeps water liquid in the inside of Pluto. And so we were astonished, all of us. The world's experts on Pluto were astonished at what we found. And that's not an unusual experience. People that were on the Cassini mission were astonished at Saturn and Titan. lakes of hydrocarbons on Titan. The Mars Curiosity mission sends us back things every week or two that are just mind-blowing. And then, of course, we got the exoplanets we've been talking about. We just keep learning and being astonished at what we find. And it doesn't stop. I mean, there's no inclination at all that the universe is going to stop surprising us anytime soon. And
but
so,
I like that. It's that astonishment is the offset against the parochial thinking that we typically have. I mean, even the Goldilocks zone, which we always talk about, where could a planet that supports life actually exist? Even that is, again, that's a very parochial way of thinking of what life is and how it would develop, how it would form. And so, what you're talking about, I think that this is the perfect way to cap off this book and to cap off the conversation is to say, look, be astonished. Keep looking. We have no idea. The biggest thing that we can contribute to future generations is to tell them, even though we know all these things, and even though we've developed our technology and our procedures to the point that we can make these astounding deductions about such distant objects, we don't know what we don't know yet. And
we're as a civilization, we're in kindergarten.
Yeah,
we're in preschool. We're not there yet, but we're getting there rapidly. Or at least we're learning rapidly. Where is it going to end up? We don't have a clue. But like I said, the next few decades are going to be very interesting to follow. But that thrill of discovery is something I wish that there was some way of sharing, especially with students, because once you've had it once, you never forget it. And it becomes hard to explain. It's hard to articulate. And I'm always disappointed with myself at describing that sense of what it's like to discover something elsewhere that you didn't expect. But yet it's one of the most important things I think that we learn in our exploration is that the universe is an incredible, 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 incredible place.
We have been on a journey of discovery with Professor Mike Summers. He, of course, is at George Mason University in Virginia, and he is the co-author of Exoplanets, Diamond Worlds, Super Earths, Pulsar Planets, and the New Search for Life Beyond Our Solar System. If you want to participate in that discovery, I'd suggest you pick this book up. It is one of these rare books that talks about something that is incredibly complex, incredibly complicated, and yet puts it in language that most of us can understand. It is an absolutely fascinating study of the planetary sciences. Mike, I want to thank you so very much for being our guest here on Triangulation. If you could, please tell our audience where they can find you, where they can find your work, and where they can find more about your passion for this discovery.
Yeah. Well, as you mentioned, the book is on Amazon. I'm at George Mason University, and I teach and do research there. In terms of finding out about what's going on in this field, I think the best place is the NASA website. It has links to all the major missions that NASA's involved in, the Kepler mission, the James Webb, the Hubble. You're going to find links to the plans for tests and for the future, even more impressive missions. Many of the discoveries that are related to NASA are announced on that website. And then there are links from there going all over the place. But I usually stop there first when I'm looking for information about a new aspect of planetary sciences or astronomy that I'm not familiar with, because very quickly you'll come up to date on what the most recent issues or discoveries are, and you can jump right into the literature from there. So the NASA website, I think, is just www.nasa.gov is really a good starting point. And of course, I love communicating by email with students or anyone, and I do this almost continually. These discussions, I think, are very important in our own growth and appreciation of the universe. But sharing this is something I think that we really can do a better job of. We can do a better job of sharing the thrill of discovery and what we're discovering and explaining the consequences for people who are not involved in this.
Professor Mike Summers, thank you very much for sharing your story, for sharing your knowledge, and of course, for sharing your sense of amazement. I think that's something that all of us could use a little bit more of in these days. Thank you very much for joining us.
My sincere pleasure. Thank you for the invitation.
And of course, folks, you can find us every Monday at 10 o'clock a.m. Pacific time for Triangulation, where we will bring back a new guest every week to share a little bit more about this world in which you live. You can find us on Twit TV at our show page at twit.tv/try. That's TRI for triangulation. Of course, normally it's going to be with Leo Laporte, but we will try to bring you the most fascinating guests that we could find to help explain the world of science and technology that's around you. Until then, I am Father Robert Ballecer, the digital Jesuit, saying we'll see you next time on Triangulation.